this lecture, we're going to look at sections 5.1 and 5.2 out of the book. We're going to start by talking about induction. Induction is a very powerful proof technique, particularly for computer science. In computer science, we have a lot of recursively defined algorithms. We want to do certain things like put an upper bound on the runtime, or it's kind of worst case scenario runtime for our algorithm, and we would like that to be small, and so you'd like to prove certain things about it. And typically in those situations, you find your upper estimates for the runtimes are recursive, and you want them not to be recursive. So your worst case scenario runtime for a certain algorithm is defined for a certain input size is majorized by your worst case running time for algorithms for smaller input size. And in those situations, you want to go from a recursive upper estimate to an explicit one. And in those situations, something called the substitution method is useful. And substitution method is an application of proof by induction. So we're going to talk about proof by induction. So, inductive reasoning, if you just think about the origin of the word, inductive means to go from the specific to the general, if that kind of helps you understand what we're trying to do here. So remember predicate functions. So predicate functions are defined on some universe or some domain or domain of discourse. Those were different names that we had for the same thing. A predicate function takes inputs from the domain, and for each input we have a proposition as the output. So here I have, just for the sake of having a concrete discussion, I've said assume our predicate function p is defined on n, the set of natural numbers, and by that I mean 1, 2, 3, 4, 5, etc. However, induction doesn't have to be on n. It could be on the set 0, 1, 2, 3, 4. It could be for, it doesn't have to start at 1, it can start at 5. Okay, so maybe I could have a P5 and P6 and P7, but no P4. Okay, so, but just for the sake of having a concrete example, I have n here. So, predicate function that we might have would be the statement Pn is the statement that this sum equals this formula. So we've seen this. This was used on our previous test, right? This is one of our summation formulas. So this means 1 plus 2 plus ... plus n. Okay? We had an identity for how to evaluate that. So Pn might be the statement that this identity is correct. Okay? Okay. So this might look like an assertion, but we can actually think about it as a sequence of assertions. When n equals 1, that's an assertion, right? When I put a specific value of n here, it becomes a single proposition. P of 2 is a single proposition, P of 3. So I get P1, P2, P3, P4, P5, P6, and each of those is a different proposition, right? Because this is a predicate function. Right? We'd like to know, how can I prove all of them? It's an infinite sequence of propositions. How can I prove all of them? Well, you can prove them, in this situation you can prove this kind of directly, where you just take a general n and show that it's correct without any kind of outside information, without any kind of assumption about what n is. But in this situation, and in many other situations in which we have proof by induction, well, if P2 and P3 are in some sense related, and we'll see how they're related in just a minute. P4 and P5, they're related, P5 and P6. So in situations like this, where the different propositions are related to each other, sometimes we can use the information that we know. For example, if I already know P of 2 is true, then I can use that in proving that P of 3 is true. And so when there's kind of a similar structure between the propositions that we get here, induction might be a useful tool. Okay? So there are two kinds of induction that we're going to talk about, weak induction and strong induction. So they both involve two steps. So we call the steps a base step and an inductive step. So if I want to prove P1, P2, P3, P4, I want to prove all of them, and I want to use weak induction to prove it, I'm going to do two things. The first thing I'm going to do is prove P1, just by itself. Okay? We call that the base case. Okay? And I'm going to prove that if P of n is true, then P of n plus 1 is also true. So here, we have to be very careful about reading this. I'm not, in this second step here, I'm not proving that P of n is true. And I'm not proving, in an unconditional sense, that P of n plus 1 is true. The second thing, the second item to prove here, the second bullet is this, in symbols. Okay? I'm saying if P of n is true, then P of n plus 1 is also true. I'm not asserting that either one is actually true, but I'm saying that if this one is true, then this one is also true. And if I can prove both of these things, I could prove the base case, and I could prove that if P of n is true, then P of n plus 1 is true, then I get them all. Okay? So, why do I get them all? Let's kind of look here at the bottom. If I know P of 1 is true, and I know that the truth of one proposition implies the truth of the next one, then everything in the P of 1 is true because we proved it by itself. That's the first bullet point, is to actually just prove P of 1 by itself. And then I know that if this one's true, then so is the next one. And this one's true, so is the next one. And this one's true, so is the next one, and so on. And they're all true. Okay? There's another kind of induction called strong induction. Okay? So here, weak induction is called weak induction because I'm assuming less than we assume in strong induction. So for weak induction, I want it to go from knowing that P of n is true to knowing that the very next one is true. So in this case, in order to know that P of n plus 1 is true, I only assumed that P of n is true, and I didn't assume anything about like P of n minus 1 or P of n minus 2 or anything that came before Pn. Strong induction is different. I want to prove that P of 1 is true, so that's the same step as up here. I still call it the base case. And then for strong induction, I'm going to assume that P of m is true for all m smaller than n, and then I want to prove that Pn is also true. So here I'm assuming, I'm trying to know that P of n plus 1 is true if the previous one is true, right? The immediately previous one is true. And here I'm trying to prove that P of n is true if all of the previous statements are true. So this is a stronger assumption, assuming that all of the previous propositions are true and then proving the next one. That's assuming more than assuming that the immediately preceding proposition is true and then getting the next one. We'll see examples of both of these, and when we see them, we'll say this is weak or this is strong, so we can see the difference. Okay, so we just have a few examples here. So I'm going to prove the first thing that I wrote on the first page. I'm going to prove that my proposition Pn is, I have it written differently than I had it written on the first page, is n squared plus n over 2. And I want to prove that this is equal to 1 plus 2 plus 3 plus dot 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 all the way up to n. Okay? So I want to prove this by induction. We proved this in the previous notes. This is one of our identities for sums. We proved it in a previous set of notes, and we didn't use induction there, but we're going to prove it again using induction. So for proof by induction, I need to do those two steps. I need to prove that P of 1 is true, just by itself. Okay? And again, I'll remind you, induction doesn't have to start at 1. It can start at 0, or it can start at 2, or it can start at 10, or anywhere else. The base case means proving P of whatever my first n value is. Here my first n value is 1, so we're doing P of 1 first. In a minute we'll see an example where my first n value is 0, and our base case is going to be P of 0. And we'll also see a situation where my first n value is 2, and then the base case will be P of 2. The base case is just proving P of whatever the first n value is. In this case, it's 1. Right? So I want to prove that this is equal to this when n equals 1. Right? So I'll just take n equals 1, plug it in the left-hand side, and I get 1 squared plus 1 over 2, which is 1. I take 1 and I plug it into the right side, and the right side is the sum, starting at 1 and going up to, well, in this case, going up to 1. Right? The sum, I goes from 1 to 1 of 1 is just 1. It's one term there. There's only one value of I, it's 1. So the left-hand side here is 1 when n equals 1, and the right-hand side is 1 when n equals 1. So P of 1 is true. The left-hand side equals the right-hand side. They're both equal to 1. So we just, by itself, proved P of 1. Now I would like to show that P of n implies P of n plus 1. Now here I'm not proving that P of n is true. Okay? I'm not actually even really unconditionally assuming that it is. I don't really care if P of n is true for this part of the problem, but I'm just going to show that if it happens to be true, then this one is also true. Okay? So that's how we do the inductive step, is I'm going to assume P of n is true, and then prove that P of n plus 1 is true. So here, this is P of n. Right? This is the proposition P of n, and I'm assuming that that's true, and then I'm going to show that that implies Pn plus 1 is true. Right? So let's do that. So, for P of n plus 1, I want 1 plus 2 plus 3 plus 4, all the way up to n plus 1. So that's what I have written here. Okay? This is the right-hand side for P of n plus 1. 1 plus 2 plus 3, all the way up to n, and then n plus 1. Okay? So, here's where proof by induction is useful, because the right-hand side for P of n plus 1 has a lot in common with the right-hand side for P of n. So what I'm going to do here is I'm going to group these things. Okay? So I can take the first n terms, and then there's the last term, which is n plus 1. And the first n terms, right, that's just the right-hand side for Pn. Okay? And I have assumed that Pn is true, so that means that 1 plus 2 plus 3 up to n, which is the part in the first set of parentheses here, is equal to the left side here, which is n squared plus n over 2. So I've assumed this equation is true, that's Pn, and then I look at the right-hand side for Pn plus 1, and here, part of it I can see is the right-hand side for Pn. So I use this assumed equation to say, well, this part of the parentheses is equal to n squared plus n over 2, and that's where this comes from. And then the n plus 1 just stays in n plus 1. Okay. Now here, I'm going to get a common denominator. All right, so just multiply this n plus 1 by 2, and then put everything over 2, and then combine it, and you can just check for yourself that this works out to be n plus 1 squared over, or plus n plus 1 over 2. And this is the left-hand side for Pn plus 1. Right? So, if this equation is true, okay, I'm not asserting that it is true, but I'm saying if it is, then the right-hand side for Pn plus 1 equals the left-hand side for Pn plus 1, which means that Pn plus 1 is also true. So here, I didn't actually prove directly that Pn is true. I just said that if it's true, if Pn is true, which is what this circled equation says, then Pn plus 1 is also true, which is what I computed down here. Okay? So, now I have P of 1, and I have P of n implies P of n plus 1. Those two things together tell me that P of n is true for all n, because here I know P of 1 is true, I proved it. And then here, this tells me that P of 1 implies P of 2. So since P of 1 is true, and P of 1 implies P of 2 is also true. Okay? So since P of 2 is true, and P of 2 implies P of 3 is also true. Since P of 3 is true, and P of 3 implies P of 4 is also true, etc. forever. So this was weak induction. This was an example of weak induction, because here I proved that one case implies the next case. So here, if I show that P of 3 implies P of 4. Okay? And in order to get P of 4, I only needed to assume P of 3. I didn't need to assume P of 1 and P of 2 and P of 3. Okay? So for weak induction, if I wanted to get one case, I need to assume the previous case. For strong induction, I would have had to assume all of the previous cases, not just the one immediately before. Okay. So here's another formula that we already had, this geometric sum formula. For this entire page, we're going to say this r is not equal to 1 in order to make sure that these denominators are well defined. So here's an example. My predicate function is this proposition, right? So I have P of n. The output is a proposition. It is this proposition, that this left side equals this right side. That is my proposition. So P of n is this proposition. So the domain for this predicate function is 0, 1, 2. So here I have P of 0. Okay, so this is an example of a predicate function that's starting at 0 instead of 1. Okay? But I still have a base case and then an inductive step. My base case is going to be prove P of 0, because 0 is my smallest n value. That's the base case. So I'm going to prove P of 0 just like I did on the previous page. I plug in n equals 0 on the left side, and I get sum from 0 to 0 of r to the 0, which is just r to the 0, is 1. And I plug in n equals 0 on the right side, and I get r to the 0 plus 1 minus 1 over r minus 1, which is just r minus 1 over r minus 1, which is 1. So the left-hand side and the right-hand side of this proposition are equal when n equals 0. So I proved p of 0. This side is equal to 1, and this side is equal to 1 when n equals 0. Okay? So that's my base case. I proved p of 0. I proved p of the smallest n value. Now I want to prove that p of n implies p of n plus 1. So again, I'm not assuming that p of n is true unconditionally. I'm not proving that p of n is true. I'm not proving that p of n plus 1 is true. I'm proving that if p of n happens to be true, then p of n plus 1 will also be true. So we assume that p of n is true conditionally, right? Which is what this says. Right? So p of n is just the assertion that these two things are equal. So I'm assuming that that's true conditionally. Just for this part of the proof, I assume that p of n holds, which is what the box, what's in the box. Right? And I would like to prove that p of n plus 1 also holds. So what I do is I start by writing down the left side of p of n plus 1. Okay, so this is p of n, so p of n plus 1 is going to have an n plus 1 here, and that's what I write down here. Okay? Again, this is useful because the left-hand side of Pn looks a lot like the left-hand side of Pn plus 1. The only difference is P of n plus 1 has one more term, the n plus 1 term, that's not in the Pn left-hand side. So this is the sum as I goes from 0 to n plus 1 of r to the power I. Well, I could split that up into the sum as I goes from 0 to n of r to the I plus just the I equals n plus 1 value. So the first terms and then the very last one in this sum. So I split off the last term of the sum over here, and then all of the other terms are here. Now I've assumed Pn is true, and this left-hand side here is exactly what's here, so I can use that this left side equals this right side to go from here to here, and then the Rn plus 1 stays both places. And now again, I get a common denominator, work it out, and then I get this, which is the right-hand side of Pn plus 1. So, if this Pn is true, then Pn plus 1 is true, because this is the left-hand side of Pn plus 1, and this is the right-hand side, and if this part in the box is true, then this is equal to this, which tells me that Pn plus 1 is true. Okay? This is another example of weak induction. Okay? Okay, so here's an example of strong induction, and here's an example of a predicate function whose domain is not just n. Here p of n is defined for n equals 2, 3, 4, 5, but there's no p of 1 in this case. So here I'm using a predicate function, p of n, and the domain is the set of integers that are greater than or equal to 2. So my p of n is going to be the proposition n has a prime factorization. Okay. So prime factorization, so n has a prime factorization means I can write n as the product of prime numbers. So remember, a prime number is, for us, we're going to say a positive integer. So for the sake of this problem, we're going to assume all the integers are positive. For us, a prime number will be a positive integer whose only, so a positive integer greater than 1, so 1 is not a prime number. So it's going to be a positive integer greater than 1 whose only divisors are 1 and itself. Okay, so we've got to get all those definitions out of the way. I think we probably know what prime numbers are. So this one I'm going to do by strong induction. Okay, so I prove the base case. So my smallest n value is 2, so the base case is 2. So I need to prove p of 2. So how do I prove that 2 has a prime factorization? Right? So p of 2 is 2 has a prime factorization. Well, 2 equals 2. This is a product of just, well, 2 with itself. Right? So there's no other numbers here. We consider this a product of one term. You might not think that that counts as a product, but we, by convention, we agree that a product of one factor is also a product. So because 2 is a prime number, it is basically just its own prime factorization. So 2 has a prime factorization, it's just itself. Now, I'm not going to assume that Pn is true and then prove that Pn plus 1 is true. What I'm going to do is say that, assume that for some n bigger than 2, assume that P of m holds for all of the smaller m. that are also greater than or equal to 2. So for all m in my range, which are less than n, assume that p of m holds. So what that means is assume I have some number, and every smaller integer between 2 and that number, including 2 and not including the number, assume that all the m's in between have prime factorizations. We're going to prove that this number n also has a prime factorization. So, kind of covering up the kind of formal quantification of it, what I'm doing is saying if I have some number n and all of the smaller integers have prime factorizations, then n is also going to have a prime factorization. Right, so let's prove it. Okay. So here I wrote down what strong induction is in our symbols, but it's not so important. Okay. So we fix this n. There are two cases. If n is prime, then it's its own prime factorization, just like 2 was. Case 2, if it's not prime, then it's composite, right? So a positive integer that's not 1 and not a prime is called a composite. So if it's a composite, then it's the product of some smaller numbers, right? So if it's not prime, then we can write it as the product of two smaller integers. Those integers have to be between 2 and n. So we've assumed that p of m holds for all of the m less than n. And here, k and l, they are in the appropriate range. So by our assumption up here, right, our strong induction assumption, p of k is true and p of l is true. Okay? That's what we've assumed here. Okay? Okay, so if this assumption is correct, then p of k is true and p of l is also true. If p of k is true, that means k has a prime factorization, so let's write out a prime factorization. So take k and write it as a product of primes. So here there might be just one prime, right? It could be p1 by itself. That's allowed. Right? And if p of l is true, that means we can take l and write it as a product of some primes. Okay? Then n is k times l. K is this product of primes, L is this product of primes, so N is this product of all the primes, all the P's and all the Q's. That's it. We prove that if all of the integers smaller than N have a prime factorization, then so does N. Basically what we did is we took N, split it. Well, if it's prime, then we don't need to do anything. If it's not prime, then we could split it, find prime factorizations for the two factors in the split, and then just put those together into prime factorization of the whole thing. And this was strong induction because, let's take a look back to the previous thing. Here I assumed p of n, and then showed that that implies p of n plus 1. So here I went from one index to the very next index. Okay? So for example, I showed that p of 10 implies p of 11. In order to reach the conclusion of p of 11, I only needed to assume p of 10. I didn't need to also assume p of 9 and p of 8 and p of 7, etc. Here, I assumed that so if I wanted to get p of 10 here, then I had to assume p of 9 and p of 8 and p of 7 and p of 6 and p of 5 and p of 4 and p of 3 and p of 2. That's what this box said, is I assumed not just to get to p of n, I didn't just assume p of the previous thing, I assumed p of all of the previous things is true. One more quick example of induction. Okay. So this is about cardinalities, right? So remember, 2 to a set is how we denoted the power set. So here this is the set 1, 2, 3 up to n. Okay, so that's just a set. 2 to the this set is the power set, which means the set of all subsets of this set. Okay? And here this is the cardinality of it. My claim is so this thing inside the cardinality, this is a set. So 2 to the set is a set. I take the cardinality of it and I claim that that is equal to 2 to the n, which is a number. Right? And so this is my p of n. This is my proposition. But if this is it written in symbols, if I want to write it in words, I can say p of n is this proposition. This set, containing n elements, has this many subsets. Okay, so this set, 1 up to n, has this many subsets. Okay, and we're going to prove that by induction. Okay, So it's going to be weak induction again. So here I'm going to start at n equals 1. I could have started at n equals 0, but then that gets into things that have to deal with conventions that we establish, which is, I think, a little more confusing than it's worth. So I'm going to start at 1. So this set, 1, that's the n equals 1 case up here, so I want to prove p of 1. This set has two subsets, the empty set and the whole thing, and there's nothing else. Right? So I just counted this set when n equals 1 is this, and it has two subsets, and that's 2 to the 1. So this is a true statement when n equals 1, and we just proved it by itself. Yeah, there's no induction there. There's just us proving a special easy case, the base case. So now I want to prove that p of n implies p of n plus 1. And here I'm going to leave out a little bit of detail, and we will talk more about this when we get to the counting section, which is chapter 6. Okay, so I'm going to take the power set of this set. So I have the set 1, 2, 3 up to n plus 1. I want to take the power set of it. So the power set is the set of all subsets. I can split those subsets into two groups. I can look at the sets here which do not contain n plus 1 and call that A, and the sets which do contain n plus 1, and I'll call that B. Right? So here A is just the set of all subsets here which don't contain the n plus 1. Now it's pretty easy to see, if you think about it just for a minute, that this A, which is the set of subsets of this set which don't contain n plus 1, that's just the set of all subsets of 1 to n. Right? So, so this A it's the set of all subsets here which don't contain n plus 1. Well, that's just a list of all the subsets of 1, 2, 3, n. And by the assumption of p of n, A has 2 to the n many things in it. Okay? And it's also pretty easy to see, if you think about it just for a minute, that A and B have the same number of elements. As I can find a one-to-one correspondence between A and B. If I want to go from a subset of this set, which doesn't contain n plus 1, to a subset of this set which does, I'll just take a set here, add n plus 1 to it, and I get something over here. And that's a one-to-one correspondence. So I just look at all the sets over here which don't contain n plus 1, and all the sets over here which do. Then there's a one-to-one correspondence that I can take a set over here, add n plus 1 to it, and get something over here. And this is a bijection between A and B. Right? So, for that reason, I can count the number of things in B. It's also 2 to the n. So, the power set here, well, I split it up into these two sets, count the number of things in each, and add those together. There are 2 to the n things here, 2 to the n things here, 2 to the n plus 2 to the n is 2 to the n plus 1. So we prove that if p of n holds, then p of n plus 1 holds, because I showed that the set 1 up to n plus 1 has 2 to the n plus 1 subsets. Okay? So let's get a more intuitive description of why this is true. So each time we add a new element, right? So we go from the set 1, 2, 3 up to, let's say, 10, and that has 2 to the 10 subsets. Okay? And I want to know, okay, now I'm going to look at the set 1, 2, 3 up to 11. How many subsets could I have there? Well, basically, when I'm looking at 2 to the 10, or 1, 2, 3 up to 10, and I count that there are 2 to the 10 subsets, I'm saying, all right, let's look at all the things from, we look at 1, it may or may not be in a subset. So I have 2 options for 1 and 2 options for 2. 2 may be in the subset, maybe not. 3 may be in the subset, maybe not. Okay? So when I'm looking at the subsets of 1, 2, 3, up to 10, there's no 11 in there. But now if I say, okay, we're looking at subsets of 1, 2, 3, up to 11, we say, now you may or may not include 11. So we're basically doubling the number of sets. If we think about it, in the sense that we're now allowed to choose 11, well, we can choose it or not, and that gives us twice as many options as we had previously when we were looking at subsets of 1, 2, 3 up to 10, when we could not choose 11. Right? So I feel like that would be much more helpful if I could draw an interactive picture as I went through that explanation, but we'll talk more about that when we get to counting. So, I want to say one more quick thing about why induction works. It has to do with the principle of well-orderedness. So the set of natural numbers is a well-ordered set. And right here in parentheses is the definition of a well-ordered set. The fact that n is well-ordered means that every non-empty subset of n has a minimum. Right? So in order to think about the significance of a set being well-ordered, I think it's a good exercise for you to try to think of a set that isn't well-ordered. You can have a subset that doesn't have a minimum. The real numbers is not a well-ordered set. I can find a non-empty subset of the real numbers which doesn't have a minimum. In fact, the set of real numbers itself does not have a minimum. Okay? But the set of positive integers, every non-empty subset has a minimum. So, why does induction work? Is I want to look at this predicate function that we had before, any one of the predicate functions that we had before, and I want to assume that p of 1 is true, right? So that's my first assumption. And I'm assuming that if p of n is true, then p of n plus 1 is also true. Right? And I want to claim that these two things together imply that p of n is true for all n. And the proof goes like this. Well, let A be the set of n in n such that p of n is false. What I would like to know is that A is empty. There is no n for which it's false, which means it's true for all, p of n is true for all n. That's what we would like. That's the conclusion we would like to reach. So, if A is empty, then we're happy, right? That means that if A is empty, that means that there are no n for which p of n is false, which means they're true for all n, right? That's what we would like to reach. Okay? So, we want to prove that, well, the alternative, where A is non-empty, cannot happen. Okay? So, we'll do that by contradiction. Let's assume that A is non-empty, and then we'll reach a contradiction. Okay? But if A is non-empty, then it's a non-empty subset of the set of positive integers. And remember, the set of positive integers is well-ordered, which means if A is a non-empty subset, it has a minimum. Right? So let M be that minimum. Okay? So let's look at case 1. M equals 1. Well, that's not possible because we've assumed up here that p of 1 is true. Okay? But because M is in A, right? So if M is the minimum of A, then it's a member of A. A is the set of n such that p of n is false. So M is in A means p of M is false. Okay? So M can't be 1 because we know p of 1 is true. If M is 1, then p of 1 would be p of M, which would be false by the definition of A and the fact that M is in A. So M cannot be 1. Okay. And now I want to look at the other case where M is greater than 1. Okay. Then I'll let n be m minus 1. Since m is the minimum of A, here n is smaller than m, n cannot be a member of A. M is the smallest thing in A, and n is smaller than m, so n can't be in A. Okay. So that means p of n is true, because p of n is not, or n is not in A. So it means p of n is true. But up here, double star, we know that if p of n is true, then p of n plus 1 is also true. But p of n plus 1 is m. So, again, case 2 is impossible because, well, if the minimum is greater than 1, then the previous thing must be true by the minimality of m. But then that implies the next one is true, which is impossible because then here we have p of m being both true and false.